Hello, my name is Ginny Sasante, and I had the red mechanism for the teacher mechanism assignment. So, right here is our starting molecule, and here's where we want to end up, our final product. So, our clues start off with saying that there are only 2 residues in the active site that were required for catalytic activity, and loss of aspartate 45 results in 35% activity, and loss of aspartate 63 results in 30% activity. So what that means is that instead of 100% activity, which is optimal, that's we want our reaction to have 100% activity. But once we lose our aspartates, activity drops to 35% and 30%, meaning that aspartates are very important to the reaction, to the catalysis of the reaction. And so we can assume that the 2 residues that were required for catalytic activity were aspartates. And moreover, another clue we had was that our pH 100% activity took place at pH 4, or around pH 4. And we know that our aspartates have a pKa of 3.7. And we know that when pKa equals pH, 50% of the residues will be protonated and 50% of the residues will be deprotonated. And so I inferred that I would have to use one of the aspartates as a base and one of the aspartates as an acid for my reaction. And our nucleophile is going to be this water, and our electrophile is going to be the carbonyl of this cyclic amide. Okay, so we start off by using our aspartate to grab a hydrogen off of the water to make it a better nucleophile, make it more electronegative, to substitute into the carbonyl. And let's right like that. And the carbonyl electrons can grab that hydrogen to stabilize the tetrahedral intermediate that will be formed as a result of this nucleophilic attack. So already we can see that base catalysis is occurring because this aspartate has acted as a base to facilitate catalysis. It's grabbed a hydrogen. And we can also see that acid catalysis is occurring because this aspartate has donated a hydrogen in order to facilitate catalysis as well. And we can also see that the proximity effect is occurring because with them being, with the residues being in close proximity within the active site to the molecule or to the substrate, that also facilitates the reaction. Okay. So, drawing our tetrahedral intermediate. And then our now protonated aspartate and our now deprotonated aspartate. Okay. Now order to open up this cyclic amide and kick off that nitrogen group, we need our carbonyl to reform. So this aspartate is going to take a hydrogen and allow the electrons to come back into, turn back into the double bond with the carbonyl. This electron allows the carbonyl to kick off the nitrogen or the amine. And the amine, to stabilize itself, is going to reach for hydrogen from this aspartate, and that is acid catalysis that's occurring. So it's basic catalysis, because this is grabbing hydrogen. The amine is, or this is acting as a base and grabbing hydrogen, and this is acting as an acid and donating hydrogen. Okay. Also, we can see that this is a sequential reaction because a ternary complex was formed between the enzyme and two substrates. Just need to add that. Okay. So now, drawing our open ring. And then now deprotonated. Okay. Alright, now our ring is open, and since we know that our reaction occurs at pH 4, and we know that the pKa of amides are around 10, and the pKa of carboxylic acids are around 4 or 5. We know that this would prefer to be protonated at a pH of 4, and this might prefer to be deprotonated. So you can have this. Let's put it in a more favorable state. Right. And then we have our final product.